We have derived the equations of motion for uniform acceleration. In this video, we look at a few questions in which we will apply these equations. Now, the first question says that an aircraft has a landing velocity of 50 meters per second and decelerates uniformly at 10 meters per second squared until its velocity is reduced to 10 meters per second. Calculate A, the time taken to slow down to this velocity, B, the distance covered during the acceleration. We have derived the equations of motion for uniform acceleration. In this video, we'll look at a few questions in which we'll apply these equations. The first question says, an aircraft has a landing velocity of 50 meters per second and decelerates uniformly at 10 meters per second squared until its velocity is reduced to 10 meters per second. Calculate A, the time taken to slow down to this velocity, B, the distance covered during the deceleration. So what we will do is to read the question again and to write down the information that we have. So the first part of the question says, an aircraft has a landing velocity of 50 meters per second. This, of course, is our initial velocity. So therefore, our initial velocity, U, so the initial velocity U is equal to 50 meters per second, right? And decelerates uniformly at 10 meters per second squared. Now, the aircraft decelerates uniformly at 10 meters per second squared, which therefore means that the acceleration A is equal to minus 10 meters per second squared, right? So remember that deceleration basically refers to a negative acceleration. But of course, in the equations of motion, we only have acceleration. So we must basically use our negative acceleration whenever we're talking about deceleration or retardation, right? So an aircraft has a landing velocity of 50 meters per second and decelerates uniformly at 10 meters per second squared until its velocity is reduced to 10 meters per second. So this velocity now is the final velocity V. So the final velocity V is equal to 10 meters per second. Now the question asks us to calculate A, the time taken to slow down to this velocity. Alright? So in part A, we want to find the time taken T. So we look at the information that we have, what we want to find, and we try to select one of our equations of motion that we can use to find it. So we have the initial velocity U, 50 meters per second, the acceleration A, minus 10 meters per second squared, the final velocity V, 10 meters per second, and the time T, which we want to find. Now, I will just drop down the equations of motion. So for the equations of motion, we have V equals U plus AT, we have S equals U plus V over 2 times T. We also have S equals UT plus a half AT squared. We have V squared equals U squared plus 2AS. And lastly, we have S equals VT minus a half AT squared. Right? So we look at information that we have, what we want to find, and we'll select the most appropriate equation. So in this case, we have our initial velocity u, acceleration A, velocity V, and we want to find T. So if we look at our equations, we have V, we have U, we have A, and we want to find T, and therefore use the first equation, V equals U plus AT. So we can write down V equals U plus AT, and we can transpose and make T the subject, and so we get that V minus U over A is equal to T. And so therefore the time taken T is given as final velocity V 10 minus the initial velocity 50 divided by the acceleration A, which is minus 10. And so this gives us minus 40 divided by minus 10, which gives us 4 seconds. And so the time taken to decelerate to 10 meters per second from 50 meters per second at this rate is 4 seconds. So that's part A of the question. Now part B says to calculate the distance covered during the deceleration. Alright? So we still have all of this information from before. We have the initial velocity U, the acceleration A, the final velocity V, and we've now calculated the time T for which the plane decelerated, and now we must find the distance traveled basically during this time. So we have all of that information before, and now we want to find the distance traveled. Now again, we can use more than one of the equations, but we'll simply use one which probably the simple of the of all those we can use. So we can use this one because we have U, we have V, and we have T. We can also use this one because we have U, we have T, and we have A. Likewise, we can use this version as well, but that would require us to basically transpose for S or to substitute the values and then solve for S. And we can also use the last one, but we will use the second. S equals U plus V over 2 times T. So S equals U plus V over 2 times T, and this gives us S equals 50 plus 10 over 2 times 4. So we have 50 plus 10, that is 60. 60 divided by 2, that is 30. So 30 times 4, then that gives us 120 meters. So the aircraft would have traveled a distance of 120 meters when its velocity decreased from 50 meters per second to 10 meters per second. So that was the first question. We then look at question 2. Question 2. A car accelerates from rest at a steady rate of 1 meter per second squared. Calculate A, the time taken to reach 50 meters per second, B, the distance traveled during this time, and C, the velocity of the car when it is 100 meters from the starting point. So we'll read the question again, and we'll of course write down the information that we have. So the first piece of information, a car accelerates from rest, right? Now the word rest of course implies that the velocity is 0, and because it is accelerating from rest, then this means that the initial velocity U is equal to 0. So the initial velocity U is equal to 0, and we know that because you're told that the car accelerated from rest, right? We're told it accelerated at a rate of steady rate of 1 meter per second squared, and therefore its acceleration A equals 1 meter per second squared. Right? And part A of the question wants us to find the time taken to reach 15 meters per second. So in part A, we're given the final velocity V, which is 15 meters per second, and we want to find the time taken T. Alright? So we have the initial velocity, we have the acceleration A, the final velocity V, and we want to find T. And this of course means that we're going to use a version of this equation, V equals U plus AT, from which we get that t is equal to v minus u over a. And so this gives us 15 minus 0 over 1, and this gives us 15 seconds. So therefore the car took 15 seconds to accelerate from 0 to a velocity of 15 meters per second at a rate of 1 meter per second squared. So that is part A. Let's look at part B. Part B now asks us to find the distance traveled during this time. So in part B of the question, we want to find the distance traveled s. So we have all of this information from before: the initial velocity, the acceleration, the final velocity, and of course the time taken t. So once again, we can basically choose any of the equations which apply, right? So let's examine which equation we can use. Can we use this one? Yes, because we have u, we have v, we have t. We can also use this because we have u, we have t, and we have a. And we can also use this because we have all of those, v, u, and a. And we can also use this one. But of course, let's use the third. S equals ut plus a half at squared. So we have s equals ut plus a half at squared. Now the initial velocity is equal to 0. So 0 times anything gives us 0. But let's just substitute the values. This is 0 times 15 plus a half times 15 times, a half times 1, acceleration is 1, times t, which is 15 squared. So this is 0, of course. So this is 0 plus a half. Half of 1 is just a half. And 15 squared, that is 225. And so half of 225, then this gives us 112.5 meters. So the distance traveled during this time is 112.5 meters. Now part C, they want us to find the velocity of the car when it is 100 meters from the starting point. Now for part C, not all the information that would have been able to obtain or that were given from before will apply. So we'll write down the information which applies to part C. Right? So part C, the initial velocity still applies. So u is still equal to 0. The acceleration a is still equal to 1 meter per second squared. Right? And they want us to find the velocity of the car when it is 100 meters from the starting point. So this means that the car would have traveled a distance s is equal to 100 meters, and they want us to find the velocity, right? So they have traveled a distance or a displacement of 100 meters, and they want us to find the velocity. So again, let's look at what we have, what we want to find, and see if there's an equation that we can use to find it. So we have u, we have a, we have s, and we want to find v. So that means you can use this equation, v squared equals u squared plus 2as. So we have v squared equals u squared plus 2as. And so we have v squared equals 0 plus 2 times 1 times 100. And so v squared is equal to 200. This will be meters squared per second squared. And so v is equal to the square root of 200 meters squared per second squared. And this gives us about 14.1 meters per second. All right? Square root of 2 is approximately 1.41 times square root of 100 is 10. So 14.1 meters per second. So this velocity is 14.1 meters per second having traveled a distance of 100 meters. And that was question 2. Now let's look at a third question. So, question 3. When the brakes of a car are applied in a car which is moving at 40 meters per second, the speed is reduced to 25 meters per second over a distance of 140 meters. If the retardation remains constant, what further distance will the car travel before coming to rest? Sketch a velocity time graph of the motion. So we'll start again and we'll write down the information that we have. So what is the first thing we're told? When the brakes of a car are applied in a car which is moving at 40 meters per second. So this 40 meters per second represents the initial velocity, u. So we write u equals 40 meters per second. Right? So when brakes are applied, the speed is reduced from 40 meters per second to 25 meters per second. So that we let our final velocity v equals 25 meters per second. And we're told that this takes place, or this occurs over a distance of 140 meters. So therefore s equals 140 meters. Now, the question goes on to say that if the retardation remains constant. So, retardation is basically another word for deceleration. And of course, it means that we are going to be required to find the acceleration, right? So, we'll first need to find the acceleration A. So, again, we look at the information that we have, what we want to find, and we'll find an appropriate equation to do so. So we have the initial velocity u, final velocity v, distance traveled s, and we want to find a. So we use equation v squared equals u squared plus 2as. So we have v squared equals u squared plus 2as. We can transpose right away to make a the subject, and so we get that v squared minus u squared over 2s is equal to a, right? So now we can substitute the values into the equation, and so a is equal to 25 squared minus 40 squared divided by 2 times 140. And this gives us 25 squared, that is 625, minus 40 squared, which is 1600, divided by 2 times 140, which is 280. So this gives us 625 minus 1600, that is giving us minus 975, and we're dividing that by 280. I'll have to work that out using a calculator. So 975 divided by 280, that gives us minus 3.48 meter per second squared. So that means the car is decelerating at a rate of 3.48 meters per second squared, right? Now the question asks us, if the retardation remains constant, what further distance will the car travel before coming to rest, right? So we found this retardation, or the acceleration, right? And they want us to find the further distance that the car will travel before coming to rest. So initially it was moving at 40 meters per second. The brakes are applied and the velocity reduced to 25 meters per second, and this took place over a distance of 140 meters. So that's basically stage 1 of the motion. Stage 2 of the motion now will deal with the initial velocity at 25 meters per second. And because the car is coming to rest, then that means the final velocity v is equal to 0. Now they told us that if the retardation remains constant, and therefore this means that the acceleration a is still equal to minus 3.48 meters per second squared. And so we have a equals minus 3.48 meters per second squared, and we want to find the distance traveled s. So we have u, we have v, we have a, and we want to find s. And to do that, we use this equation, v squared equals u squared plus 2as. So we have v squared equals u squared plus 2as. And right away, we'll make s the subject. And so we get that v squared minus u squared over 2a is equal to s. And so s is equal to 0 squared minus 25 squared over 2 times minus 3.48. And so s is equal to minus 625 divided by minus 6.96. And this gives us 89.8 meters. So the car will travel a further 89.8 meters before actually coming to rest. Right? Now, the last part of the question basically asked us or told us to sketch the velocity time graph for this motion. Now, let's basically look at what is happening. The car was initially traveling at 40 meters per second. The brakes were applied and it decelerated to 25 meters per second at a rate of 3.48 meters per second squared. Now, this is a uniform deceleration. And for the next part of the journey, it's going to decelerate uniformly to rest at the same rate. So basically, this graph will be a straight sloping line. So we have the velocity, v, in meters per second, and we have the time taken, t, in seconds on the x-axis. So essentially, it is decelerating uniformly from 40 meters per second to rest at a rate of 3.48 meters per second squared. So the graph is simply a straight line sloping downwards. Right? And this value right here would be 40. So the only thing that we need to find now is the time that it took to basically decrease for its velocity to decrease from 40 to 0. And because the acceleration is uniform, we could basically treat it as one uniform motion. So for this case, we want to find the time taken t. We have the initial velocity, let's say 40. We have the final velocity 0. And of course, we have the acceleration minus 3.48. And to find the time taken, we use t is equal to v minus u over a. And this gives us 0 minus 40 divided by minus 3.48. So this is equal to minus 40 divided by minus 3.48. And this gives us approximately 11.5 seconds. So 11.5 seconds. So therefore, the entire journey took a time of 11.5 seconds. And basically, this is a graph of the car's velocity versus time. Or you could say a graph of the car's velocity time graph. Right? So that was question 3. We'll look at one last question. All right, so question 4. Question 4 says, a sports car moves from rest with uniform acceleration to reach a velocity of 25 meters per second in 6 seconds. It then maintains this velocity for a further 12 seconds, after which it is uniformly retarded until it comes to rest 38 seconds after the start of the motion. Sketch a velocity time graph of the motion and use it to calculate A, the initial acceleration of the car, B, the final retardation, and C, the total distance traveled, and D, the average velocity for the car's motion. Right? So we start again and identify the information that we have. So basically the question asks us to sketch a velocity time graph. and use the graph to perform certain calculations, right? So the sports car, it moves from rest. So we know that means that the initial velocity is 0, right? So we have velocity in meters per second on the y-axis, and we have time taken in seconds on the x-axis. So this car, it started from rest and is going to accelerate to a velocity of 25 meters per second in a time of 6 seconds. So we show that by a straight line sloping upwards, right? So let this value here be 25, and it would have taken a time of 6 seconds, right? So this shows the sports car accelerating from rest uniformly to a velocity of 25 meters per second in a time of 6 seconds. The next piece of information we're told is that it then maintains this velocity for a further 12 seconds. So further 12 seconds. So it maintains the velocity, which means that the velocity is constant and is represented by a horizontal line or a line parallel to the time axis. Right? It maintains this for further 12 seconds, which means that this time would correspond to 18 seconds. Right? Lastly, we're told that it comes to rest. It is uniformly retarded and comes to rest 38 seconds after the start of the motion. So up to this point, it had been traveling for 18 seconds. So if it's going to come to rest 38 seconds after the start of its motion, we need to basically make sure the graph is somewhat reflective of that. So we need to extend the time axis a little bit more. Right? So yes, and so because it comes to rest a total of 38 seconds after it started, that means it will take a time of 20 seconds to decelerate from this 25 to rest. Right? So, sorry, not 25, but 20. Right? So this value here would be 38. So this is t in seconds. And that's basically the graph of the car's motion. So again, let's describe it. So this region, it accelerates uniformly from rest to a velocity of 25 meters per second in a time of 6 seconds. It maintains this velocity for a period of 12 seconds or further 12 seconds, so up to 18, after which it decelerates uniformly to rest, coming to rest 38 seconds after it began its motion. All right? So let's look at what they want us to calculate. They want us to find the initial acceleration of the car. So the initial acceleration, of course, corresponds to this region, right? So part A, the initial acceleration A. Now, how do we determine acceleration from a velocity time graph? The gradient of a velocity time graph will give us the acceleration. So essentially what we're going to be finding is the gradient of this portion here, which of course is the same thing as using the equation A equals V minus U over T. So there's a change in velocity divided by the time taken, which essentially gives us a gradient of this section. So this gives us 25 minus 0 divided by 6. And so this gives us 25 over 6. 6 into 25 goes 4 and 1 6. So this is equal to about 4.17 meters per second squared, right? Acceleration, meters per second squared. Good. Part B. So part B asks us to calculate the final retardation. Now retardation is another word for deceleration, which of course implies that the body is slowing down. And that corresponds to this region here. So the final retardation is obtained from this region. But of course we first calculate the acceleration for that region. So we have A, again, V minus U over T. And so this gives us final velocity 0 minus 25 divided by the time, which is this interval, which is 20 seconds, 20. And so we have minus 25 divided by 20, which gives us minus 1.25 meters per second squared. Now, this is the final acceleration, or the acceleration for the slowing down phase. Because the question asks us for the final retardation, or the final deceleration, final retardation, then simply the final retardation is this value, but without the minus sign. So the final retardation is equal to 1.25 meters per second squared, right? So usually when you use the word retardation or deceleration, the minus sign is not included, because that is understood as a negative acceleration, right? So you normally see that a body may decelerate or retards at a rate of, say, 10 meters per second squared, but that corresponds to a negative acceleration, right? And for part C, they want us to find the total distance traveled. So since we're talking about a velocity time graph, then the total distance traveled is actually equal to the area under the graph. All right? So we can find the total area under the graph, and this will actually give us the total distance traveled. So this first section, of course, is a triangle, is a rectangle, another triangle. We can find the individual areas of each section and then add them up. Well, of course, you could also use the formula for the area of a trapezium, but let's do the section by section and then add them all up, right? So this piece, of course, is a triangle. So this is going to give us base by height over 2. So this is 6 times 25 over 2 plus, this is a rectangle, so we have base by height. The base is 12, height is 25. This is plus 12 times 25. And the third segment, which is another triangle, the base is 20, height is 25. So this is plus 20 times 25 over 2. And let's work that out. So 6 times 25, that is 150. 150 divided by 2, that gives us 75. So I'll continue it here. So the total distance traveled S is equal to 75 meters plus 12 times 25, that is 300. So this is plus 300 meters plus 20 times 25, that is 500, divided by 2, that is 250. So plus 250 meters, right? So 300 plus 250, 550 plus 75, that gives us 625 meters. So the total distance traveled for the entire journey is 625 meters, right? And lastly, part D wants to calculate the average velocity. So the average velocity, of course, is equal to the net displacement divided by the time taken, right? So the average velocity is equal to the net displacement divided by the time taken. Now in this particular case, because the car did not go in the opposite direction, and how do we know that? The velocity, of course, remained on or above the time axis. It did not become negative, which would have indicated that it's changed or reversed directions. And so just go in the same direction, and so the net displacement would be equal to the total distance traveled, right? So this gives us 625 meters. That is divided by the total time taken, which is 38 seconds. And this gives us 625 divided by 38, which is approximately 16.4 meters per second. All right? So this, of course, is the average velocity for the car's entire journey.